18, we're going to get into the nitty-gritty for reaction rates and what happens at the molecular level for a reaction to happen fast or slow. So we're not going to do as much, but we're going to talk about how they double and triple and all that kind of stuff. We're also going to talk about reversible reactions, which we haven't discussed very much yet this year or at all, and equilibrium and what that means and how we can change it. So some reactions happen really quickly, like when you strike a match. That happens almost instantaneously, while others occur more slowly, like when biomaterial is turning into coal. That's why we call it a non-renewable resource, because it's kind of hard to depend on because it takes so long. So these are two examples of the many types of reactions that can vary from very fast to extremely slow speeds. Speed is an example of a rate. A rate is a measure of how much something changes within a specified amount of time. The interval of time can vary from less than a second, like microseconds or milliseconds, to centuries. In chemistry, the rate of a chemical reaction, or what we call the reaction rate, is usually expressed as the change in the amount of reactant or product per unit time. The amount of a reactant is usually expressed in moles. So over time, the amount of a reactant decreases and the amount of the product increases. So this is an equation. I just wanted to point this out, that this is a forward reaction that we're still talking about, and we're going to be watching or talking about reversible reactions coming up in a couple days. So a model that we use to determine and talk about how particles react is called collision theory. So according to this theory, atoms, ions, and molecules can react to form products when they collide if the particles have enough kinetic energy. So they only can react if they have enough energy. If they don't have enough energy, they will just bounce off each other and go back apart unchanged when they do actually interact. And so the whole point of this is that we can only have reactions if things are hitting each other, colliding. So this is a picture, you have it in your notes, explaining kind of how the collision process works, where if we have two reactants and they're moving too slow, so they don't have enough energy, they're just going to bounce apart unchanged. Well, not only does having enough energy play a factor, but we also need to have the molecules arranged in the right way. So in the second line, they do have enough energy, but notice how they have been flipped. And so because they've been flipped, maybe when they bounce together, the NO3 doesn't need any more oxygens, and so they bounce apart unchanged. So in order for the reaction to happen, they have to have enough energy, and they have to be arranged correctly in order to make a chemical reaction occur, according to the collision theory. The minimum energy that the particles need in order to react is called activation energy. This is a barrier that the reactants have to cross before the products can be formed. So this graph, we're going to see a couple of these, and this is an energy graph showing how much activation energy a reaction needs in order to change from reactants to products. So the reactants are always found on the left side and products are always found on the right. And notice how this line is extended from the reactants, because how much energy you need to start, the activation energy, is how much energy is needed from the beginning amount of energy for the reactants until you get to this top peak, where that's where it gets over the hump to turn into the products. And then the overall change in energy is the change, the products minus the reactants, like what we did in chapter 17, the delta H, the change in enthalpy. So to find that, you would take the products minus reactants, or just look here on the graph and see that dip. Sometimes the products are lower and sometimes the products are higher. It all depends if it's endo or exothermic. When two reactants particles collide, they can form an activated complex, sometimes. An activated complex is an unstable arrangement of atoms that forms for a moment at the peak of the activation barrier. So make sure you label this in your graph on your paper, that the activated complex is located at the tip top of the activation energy peak. Okay, so anything to the left of the peak are reactants, and anything to the right are the new products. You're going to need to label that on a graph. So the activated complex is just a big, huge molecule where all the reactants are combined together before they break apart into the new compounds for the products. So this only happens if they have enough energy and they're arranged properly, oriented properly, and so sometimes the activated complex doesn't even form. But it is so brief that we call it a transition state, and we don't write it in chemical equations. So now we're going to talk about the factors that affect reaction rates. In every chemical reaction, it proceeds at its own pace. Some are naturally fast, like we saw with the match striking, and some are naturally slow under the same conditions. However, the rate of almost any reaction can be modified by varying the conditions. So things that we can vary to affect the rate would be temperature of the reaction, the concentration of the reactants, particle sizes, and the use of a catalyst. To change the temperature, usually raising it will speed up a reaction, and lowering it will slow it down. Back in chapter 3, we learned that temperature is a measure of the kinetic energy something has. So this is telling us that if they're raising the temperature, that means there's more energy, so the particles will move faster. Which, if they're moving faster, that will make the amount of collisions that are happening increase. So if there's more collisions, then there's more chances for them to collide and make the products. So this actually gives us enough energy to slip over the activation energy barrier, and it causes the products to form faster. Another way to change is to increase the number of particles. So concentration in chemistry, usually we use molarity, moles over liters, like we learned about in chapter 16, but you can increase the number of particles in the same amount of volume, and that will affect the rate at which reactions occur. Because more particles in a fixed area or a fixed volume will increase the collisions, which will increase the turnover to products. Just like when you're walking down the hallway, if you're walking during a passing period, there's a lot better chances of running into people because there's a lot more people in the hallway, versus when you're walking during a class period when maybe only 1 or 2 people are out there, and hopefully you don't run into them. So, and then this is a picture of a flame test where, with the presence of oxygen, it's a fuel to burn fire. So if there's less oxygen particles present, the fire is not as big compared to when you have many oxygen particles present. Particle size. The total surface area of a solid or liquid can affect the rate of reaction. The smaller the particle size, the greater the surface area, and the greater the surface area, the more places for reactions to occur. So when I'm doing something in lab, I like to use smaller pieces when I have to dissolve them because it would take less time. Also, like if you're melting butter on the stove, if you just throw on one stick, that's going to take a while. So you like chop it up into little pieces to make it have more surface area, smaller particles, it goes faster. If you can't increase the surface area necessarily by chopping it up, then you can always dissolve it. This is why we use a lot more solutions in chemistry than we do solids, and that's because in a solution the particles are already separated, and so they're more accessible for the other reactants to react with them. But sometimes, like we learned in chapter 11, things cannot be dissolved. They're insoluble. So if it can't be dissolved, then it can always be ground into a fine powder to increase the surface area. The last factor that can change the rate of reaction is using a catalyst. And sometimes you use a catalyst when the temperature is not always supposed to be raised, or it might not be the best for that reaction. So remember, a catalyst is a substance that increases the rate of reaction without being used up during that reaction. Catalysts permit reactions to proceed along a lower energy path, which allows the reaction to need less activation energy to form products. So in this graph, what you have in your notes, the top line, or the solid line, is the normal curve that you would have for the reaction. But with a catalyst present, we have the dotted line where the reactants and products lines are still the same, but the activation energy peak is what has changed. And notice how it's a lot smaller. And so that's showing how you need a lot less energy to get the reaction to go. So a catalyst is great, but it's not consumed during a reaction, so it doesn't actually appear as a reactant in the chemical equation. Normally we'll write it above the arrow, so we can still know that a catalyst was used, but it's not for the actual reactant. So this is the end of video number 1 for chapter 18. The rate of reaction assignment has numbers 1, 2, and 3 that can help you with this.